And thanks to, well, okay, yes, hold on, let me just acknowledge the recording. Okay, got it. Yeah, thanks for inviting me today. And yeah, I'm going to be talking about a bit of the story behind the OSCA book that we prepped over, that we created over the past few years. Oops. Okay, oops. Let me get back on this. All right, so yeah, what is the OSCA book anyway? The OSCA acronym stands for Orchestrating Single Cell Analysis in Bioconductor. Okay, so the Bioconductor part isn't part of that acronym, but that's okay because otherwise it would look a bit weird. So if anyone hasn't seen this before, you can go to this link and check it out. So bioconductor.org/books/release/OSCA. But basically, it contains descriptions for the various steps in the a sort of routine single-cell RNA-seq analysis. So this includes basic stuff like data loading, quality control, normalization, and so on. Some more advanced stuff like cell type annotation, doublet detection, and batch correction. And it also contains end-to-end workflows for a variety of different data sets to show people how it's done. So you can just copy and paste code directly from those workflows if you want to use that in your own analysis. There's a strong focus on bioconductor packages for single-cell analysis, obviously. So the scope is, in theory, any bioconductor package that can accept a single-cell experiment object, which is Bioconductor's standard representation for single-cell datasets. So if you're a package author that has a single-cell experiment accepting package, then you could consider contributing to this book. One key feature of this book is that it is recompiled regularly by the Bioconductor build system. So the reader can be sure that all of the code examples are still working with the latest versions of all Bioconductor packages. The book itself is written in the form of multiple R Markdown files that's built using the bookdown package from RStudio. So the book process goes through all the R Markdowns, runs the code, reports the results, and creates a nice looking HTML that we can stick on a public server somewhere to allow people to read. This format is nice because it allows us to incorporate the code, the results, and the explanatory text into a single reading experience. The compilation itself is mostly straightforward, but there's a few cool tricks that I'll talk a bit about in a bit more detail later on. Right, okay, so on to the history lesson behind OSCA. So a long time ago, during my postdoc, I created this simple single cell workflow package to show people how to use my various bioconductor packages for routine single cell RNA-seq analysis. You can think of these workflow packages as a precursor to the books. Each workflow was written as an R Markdown vignette that was regularly recompiled on the Bioconductor build system. So there's a lot of similarities in terms of infrastructure. The content of each vignette was also pretty straightforward as well. I would show people how to load in the data set, run some various analysis steps, explain a bit of the theory behind each step, and then display the results. And in fact, the simple single cell package still exists, but as you can see from this overly dramatic description on the Bioconductor landing page, it only lives to redirect users to the new OSCA website. Now in the beginning, sometime in 2019, I was contacted by Rob, who was writing up a manuscript on what else but how to analyze single cell data in Bioconductor. So he wanted to create a companion book that readers could refer to with code and results and stuff that obviously wouldn't fit inside the manuscript itself. So he had seen the simple single cell workflow and he wanted to work with me to write this book. At first, I was like, I didn't want to do it because I was busy. But when I thought about it a bit, I eventually agreed to do it for several reasons. The first was to avoid having sort of fragmented repositories of knowledge of how to do single cell analysis in Bioconductor across multiple different documentation sources. So by having this book, we could just consolidate everything into a single source, which simplifies the education and onboarding of new users. The second reason was to distribute the maintenance and development of new chapters in the book to more people in the community, right? Rather than me being responsible for the simple single cell workflow package. Well, that was the hope anyway. So we got started by basically taking all of the simple single cell R Markdown files and then dumping it basically verbatim into the book in combination with some chapters that Rob had already written. This involved a little bit of reorganization because we basically now have one chapter for each analysis step rather than one chapter for each data type, which is what the previous organization was. And that sort of reorganization allows us to better discuss the theoretical aspects and parameter choices of each analysis step. We also added a lot more examples of end-to-end analyses with different data sets of different sizes and different biology, which incidentally drove an expansion of the resources available in the scRNA-seq experiment hub data package. So at the end of the year, the book was in pretty good shape. Rob's manuscript had run the gauntlet of Nature Methods, and I was nicely tucked in as the second author here. So basically win-wins all round, right? But then the troubles began, right? So over the course of the next year, in 2020, the book had ballooned to about 30 chapters, and it had become basically impossible to build. So this occurred for a variety of reasons. We'd been using the Fred Hutch's servers to compile the book, and there were just a lot of problems all of the time. So I don't remember all of them. I've listed a few of them here. And sometimes the jobs would fail because the packages, the C and C++ code was compiled on one architecture and the cluster scheduled the execution on a different CPU architecture. Sometimes there were failures due to the network connections. Sometimes the BIC file cache was corrupted by parallel access. And sometimes I just broke stuff because I was updating my own packages, and the book wasn't updated as well to reflect those changes in the underlying package and the packages that they were using. So now some of these issues were sporadic, but when the book is so large, the survival rate of a build across all the chapters is going to be very low. There's probably at least one chapter that will throw an error because it can't connect to the network, or because the cache was being contested or whatever, and that's enough to break the entire thing and stop compilation. The consequence of this instability was that we could count the number of successful builds on the Hutch's servers in one hand. Well, maybe two hands, I can't really remember, but it was a single-digit number of builds. And this was attempting to build it every day for maybe a year. And it was really actually a major event when we were able to get a successful build, because that's how rare it was. So I tried a bunch of things to get around this. I tried moving the compilation over to the Genentech servers, but that didn't help because R's parallelization strategy kept on causing the jobs to run out of memory and then get killed by the out-of-memory killer that we have that controls the resources on the cluster. And then, at the end, I just gave up and just built the book on my laptop while doing my grocery shopping. So basically, it'll just run for 2 hours building the book, and then I just manually push it to GitHub pages. And then, and it didn't. I can't really blame him, but it also didn't help that Rob had a baby at the time, if I remember correctly. So I was kind of left holding the can for trying to get this thing to build. Right. So. In about 2021, I believe, maybe the start of 2021, I had enough, right? And then I worked with Hervé to get the compilation onto the bioconductor servers. This involved reformatting the book to trick the build system into running book down, as well as splitting the book up into several sub-books for easier compilation. And I'll talk a bit more about that later. And at the end of the day, this gave us a more stable and consistent build, and failures were much rarer. And then last year, I think late last year or mid last year, the OSCA source code itself was finally transferred to the bioconductor core team. And each subbook got its own maintainer from the various members of the bioconductor community. From memory, I've listed Pete, Ludwig, and Alan here. Apologies if I've forgotten anyone. But at this point, I was super burnt out and I was too tired to deal with it. So it's good that some other guys were able to step up at this point. Yeah, so right, with that History Channel special out of the way, let's have a look at the architecture of the book. So yeah, each book is structured as an R package. It doesn't have any functions, it doesn't have any man pages, but it does have a lot of R markdown files. So for example, here you can see that inside the package we have the feature selection, marker detection, clustering, etc., etc. All of this. Basically, the book contents are stored inside the package. Yeah, so the book itself is stored inside the. Can you see my mouse? Is this mouse visible?
Yeah, we can see it.
So, all right, great. So yeah, the book itself is basically a book down directory that's stored inside the inst book subdirectory. We can't actually store the R markdown files in the vignettes subdirectory because they just get rendered as vignettes using R markdown rather than using bookdown. Perhaps there might have been a way to trick R command build to use bookdown render rather than R markdown render. I don't know. I wasn't an expert in trying to figure that out. But instead, what we did was that we created a makefile inside the vignettes subdirectory. And happily for us, R will execute that makefile during the package build process. And it's this makefile that contains the instructions to call bookdown on the inst book subdirectory, thus giving us the compiled HTMLs as part of the standard R command build process. The BIOS build system can then reach inside the build package, extract the HTMLs, and then post them on the server so that people can read them. I will say that we still need a stub file, a stub R markdown file, because R command build will only respect the makefile if it detects that there is a vignette that could be compiled. So that's why this stub exists. Yeah, and I'll talk a bit more about these indices for linking in a few slides. Now, as I mentioned previously, the first version of the OSCA book was this monolithic beast that contained over 30, or I think it was almost 40 chapters. I remember seeing chapter 37 at some point. So quite a few chapters. So this was pretty slow to compile. And it was very fragile to errors, which made for a very frustrating build experience as an author. So any compilation failure would cause the build to crash or to error out, and it would prevent publication of whatever changes that you wanted to make. So you never actually quite knew whether your changes would make it all the way to the end and get published on the bioconductor site. So what we decided to do was to fragment the single book into multiple subbooks, each covering a different set of topics. So I think there's 5 different subbooks right now. We're basically describing topics for basic analyses, advanced analyses, and multi-sample analyses, for example. The idea here is that if one of these subbooks, if the compilation of one of these subbooks fails for some stochastic reason, like network failures or cache errors, the remaining subbooks can still be built and still be published. And then in the next build cycle, the failed subbook from the previous build cycle will make it through, if these errors are truly stochastic. And over multiple build cycles, we would eventually get all of the subbooks published, right? So it's like error correction, right? If you do it long enough. This setup makes us more robust to random failures in the build step and allows us to push out updates to the book contents more reliably. Of course, one downside of using multiple subbooks is that it's harder to link their contents together. So bookdown, if you've ever used bookdown, or in fact, even R markdown vignettes has a feature to create crosslinks within the same book. But if you want to go between books, you have to spell out the full URL manually in the markdown. Now, having to write out the link is pretty tedious, and it's not very robust to changes in the destination URL. For example, if bioconductor changes its URL, now you've got to go through all the links and manually change them. But that's pretty unfortunate, because it's very important to provide readers with links to relevant content as they're reading through your documents. So think about how boring Wikipedia would be if there weren't any links to related topics. You wouldn't nearly spend so much time on it. So to make life easier for authors when they're trying to link to content between books, we created our own link function that gets evaluated in line and inserts the appropriate URL link to a section or a figure of another subbook. So you can see this link command in the markdown here that comes from the rebook package. And then during compilation, this gets converted into this basic section 2.4 of the, in the compiled HTML. So if one were to click on this link here, it would take us to the spike in normalization section of the OSCA basic book, right? Based on the linking parameters here. So by creating lots of links between subbooks, we can integrate them more tightly together and provide the same reader experience as if they were reading through a single book, which is, much more, well, it's a much nicer reading experience when you can jump between these, jump to related topics more easily. Now, linking is only the start, though, because we can go further and share objects between different chapters and subbooks. For example, we can take a single cell experiment generated in one subbook and then reuse it in another subbook. So this is typically used to provide a pre-processed object as inputs into chapters that don't focus on pre-processing. So this means the reader isn't distracted by having to do all this pre-processing, or having to read through all this pre-processing code in order to get to the topic of the chapter. It also allows, from an author perspective, and it allows us to avoid duplicating this setup code between different chapters, and it enables faster compilation because we're just pulling the saved object generated by another chapter rather than rerunning the pre-processing code to generate that object. So we've set it up so that the code used to generate a pre-processed object is still actually available in this drop-down tab. So you can click on this. I think I'll talk about this in the next slide. You can click on this, and then people, if they want to, they can just copy and paste that code to rerun that code to generate the object. And this is nice because it makes for a sort of smooth reading experience, because if they want to follow along and do the analysis along as they read through the chapter, they don't have to jump through it. They don't have to jump to a different chapter in order to just get the object in the first place. They can just copy the code directly and start working from that chapter. And I should note that this is all automatic. The code in the dropdown is automatically extracted from the chapter that's used to generate this object. So the authors don't have to manually copy anything. Oh yeah, and this is the example. So if you click on that tab, you get basically the code that's used to generate that particular object, which in this case is a single cell experiment object for the PBMC. So yeah, that's the code. Okay, so how do we do this? So we enable the sharing by using knitter caching. So how it works, that inside the R Markdown file that we want to use to bring in a new object, we have an extract from package call from, so this function is again from this rebook package. So rebook, so when this function is called, rebook looks inside its cache directory to figure out whether or not the 10x unfiltered PBMC 4k.rmd file has been previously compiled. If it hasn't been compiled, then it goes through knitter, and it calls knitter to compile this Markdown report, and it does so with the cache equals true parameter turned on. So once this is done, what happens is that knitter will generate caches for every chunk in the 10x unfiltered PBMC 4k R Markdown file, and each cache will hold objects that were created or modified in that chunk. So once compilation is done, rebook will then look inside the requested chunk. So in this case, it's the normalization chunk, and then it will look inside it to extract out the SCE PBMC object from that chunk. and then it will make this SE PBMC object available within the context of the original R Markdown file. This extract from package function will also parse the actual R Markdown code in this 10x unfiltered PBMC R Markdown file to extract the code up to and including the normalization chunk so that it can insert it in the drop-down tab that I was showing on the previous slide. And yeah, we also need to do some careful locking just to make sure that we don't have any data races from multiple processes trying to compile the same report at the same time. So this often occurs on when you have multiple builds running at once, such as on the bioconductor build system. Right. So that was the book structure or the structure of the book packages. So let's have a look at. Let's move on to some discussion of the contents of the book, and in particular, how do we make sure that the text and the code remain consistent? So as an author, I like to make sure that if I'm talking about abstract concepts, I like to illustrate that with concrete examples. So let's have a look at this particular section of the book as a case study. So here I'm describing how differences in the normalization strategy can affect the biological conclusions. So the text here it contains some fairly abstract statements, but this is backed up by a concrete example for a specific gene, which is MALAT1. So this concrete example involves referencing a figure that uses MALAT1 to illustrate the general effect that I was talking about. So if anyone's interested, I was basically saying that one normalization strategy, you can see differences in expression, and in another normalization strategy, those differences disappear. But yeah, that you don't have to worry too much about that. Well, as in you don't have, that's just an example. So this figure is basically generated live by the code that's listed up here. So that's also explained, sort of displayed in the compiled HTML. And all in all, I think this is a great concept. It's a great approach to teaching a concept, right? So readers get the general concept from the text, and then a concrete demonstration of the relevance of that concept with a very specific example. However, it introduces a very tight coupling between the text that we wrote and the code and results, because now we have to make sure that everything is consistent with each other. And this consistency can't be taken for granted when you're recompiling the results live, basically. For example, what if, in some future iteration of the build cycle, the log norm results function changed its behavior? What if the underlying data set on Experiment Hub was updated, right? If these changes altered the plot, then the text might not match up with the results anymore, and then the readers would be confused, and as the author, I'd look like an idiot, right? So we need a way of ensuring consistency between the text and the results, and we do that by inserting what I like to call fail-safes into the book code, basically. So these fail-safes are effectively unit tests for the analysis code inside the book. They check for consistency between the results and the text, and they trigger an error if that consistency is not met. So let's have a look at this example. Here I'm talking about the choice of the number of neighbors in graph-based clustering. The idea is that more neighbors should result in broader clusters as the graph is more tightly connected, and smaller neighbors, fewer neighbors result in finer clusters. At least that's what the text says anyway. Now, this text is followed by some code to demonstrate this effect to the user. So we run clustering with different choices of K, and we show the number of cells in each cluster. This code is then in turn followed at the end by our fail-safes. Our fail-safe test, which basically check that lower values of K actually yield more clusters that are smaller, and larger values of K yield fewer clusters that are larger. So if this is not the case, the compilation fails because these stop if not statements throw an error, and then the maintainer has to go in to figure out what went wrong. In this manner, we basically ensure that the book will only successfully compile if none of the fail-safes are triggered. which is a bit tedious to go in and have to check that why the fail-safes failed. But on the whole, I think it's better than the reader getting confused by text that doesn't match up with the results. Yeah, so this is just one example of the fail-safes. There's lots of examples of fail-safes littered throughout the book. So here's one for checking the cell type identity of a particular cluster. So cluster 1, I say in the text, cluster 1 probably contains natural killer cells. And this is checked by checking that the cluster 1 actually indeed contains the markers for natural killer cells and no markers for T cells. And yeah, this matches up with the text where I say that they're NK cells. So here's another example to check that the particular cluster contains memory T cells, in this case, based on that cluster having the maximum CCR7 expression across all clusters. And again, that makes sure that I'm consistent with the reference of the reference to memory T cells in the text. Now you might say, why not just avoid mentioning cell types in the text? Then you wouldn't have to do any of these checks, right? The problem if you do that, the problem is that if you do that, the text becomes really abstract and detached from any biology. You don't actually tie it into concrete examples. Like just to show you how difficult it would be to read. Imagine trying to write a paper where you're not allowed to talk about any concrete results, but you can only hand wave your way through with generalizations. All right, maybe that describes 90% of single cell papers out there, but I don't think that's a good reading experience, right? So if you actually want to write about real results, and the results are always being regenerated at every build cycle, then you kind of need these fail-safes to check that the results are always matching up with your text. By the way, I got all of these markers from Dr. Google, so if someone knows better, feel free to make a pull request, because Dr. Google is what I use. Right, okay. So now the existence of these fail-safes has some interesting implications in the context of the wider bioconductor ecosystem. Specifically, I'm talking about how the OSCA book interacts with the various analysis packages that it depends on. So as a package developer, I think of several types of backwards compatibility. The weakest form is when the function runs with the same call and returns the same data structure, but the contents of the data have changed in such a way that affects the scientific conclusions. For example, I might have fixed a bug in some function that computes p-values, and that just completely changes the interpretation of the results. This is still technically backwards compatible, as any code that was running using the previous version can still run using the new version. It's just that the results themselves are not kind of scientifically compatible with what they were before. The second form of backwards compatibility is that functions run as before, but return slightly different results. For example, due to changes in numeric precision or use of a different algorithm or whatever, right? In this case, the results and the scientific conclusions are still broadly compatible with what you would get from previous versions of the software. And this is the type of back compatibility that we generally see in mature packages, right? With incremental improvements and small changes to the output of particular functions. Now, the strictest form of backwards compatibility is that the functions return the exact same output down to the last byte, right? And this is the type, unfortunately, that the book needs to avoid triggering the fail-safes. So any small changes to the results can affect the rankings of various things, right? For example, the ranking of neighbors in the nearest neighbor graph, which changes the clustering, and then that changes the cluster numbers. So if the text then refers to a particular cluster as a certain cell type, it's not consistent with the code anymore. And then the fail-safes should break, right? Changes to the marker rankings can also be problematic because some genes disappear from the top set of markers, which can in turn trigger the fail-safes if we can't find the expected markers in the top 20 or 50 genes, right? And the less said about the t-SNEs and UMAPs, the better. You shouldn't rely on these coordinates at all. So this sort of reliance on strict backwards compatibility really introduces a tension between the package developers and the book maintainers, because it's very hard, if not outright impossible sometimes, for package developers to make improvements to their package while literally returning the same results. So someone's always going to be unhappy here, and as someone who was wearing both hats for a very long time, so maintaining the book and developing the packages, I was kind of always being hit by this problem on two sides. So the sort of quote unquote solution that I found was to basically stop further package development. So any non-trivial package update will break, pretty much will break the book and trigger its fail-safes, especially for something that's used very highly throughout the book, like Scran or Scuttle or Skater. And I didn't want to make all work for myself or the new book maintainers, so I just don't update my packages anymore. And this does ensure that we get very stable builds for the book, but it also holds back a lot of performance improvements from my bioconductor packages. I could actually, I keep on seeing, oh yeah, Python, we can run, these big data sets so easily. And, we could easily make the bioconductor packages run things 10 times faster if I was just free to change these packages without having to worry about this damn book, right? But I've got to keep I have to keep this OSCA plane in the air. So I can't just go in and start hacking stuff out. And in fact, I'll say that for our internal pipelines, for our internal single cell analysis pipelines, I don't even use many of my own public the sort of public packages of bioconductor anymore. I actually make a new package called Scranchan, which actually uses C++ to handle all the data representations and compute. So then I'm free to write my own code without having to worry about the sort of far-reaching implications of how that code affects the book and how that code affects like the backwards compatibility guarantees that I have to give other users. So yeah, as I said before, this book and package dilemma is not easily solved because someone is always going to be unhappy, right? The current situation makes package developers unhappy because they can't change anything. Book maintainers are reasonably happy because they don't have to do much, but users are now somewhat unhappy because they're stuck with slow code, but whatever, at least it runs. We could weaken the fail safes or reduce the coupling between the text and the code, but then users would be pretty unhappy because they would get, the book wouldn't make much sense anymore. Book maintainers would be slightly unhappy because they would have to retroactively patch the book based on user feedback when users based to deal with these confused users. Package developers now don't even have to care, right? I think one approach that I've thought about is to generate the text dynamically based on the results. So for example, you could automatically detect which cluster looked the most like the NK cells, and then you could insert that cluster number into the text. So this would be pretty painful metaprogramming. So it would be a bit of work for the book maintainers, but then it would be more robust to changes in the underlying packages, and package developers would be more free to update more quickly. And the final approach is just to freeze the book to a single BIOS version. No effort required once compilation is done. But then obviously users would be quite unhappy because as soon as the book goes out of date, it doesn't make any sense anymore. I think, personally, no, there was an arrow that was meant to appear. There it is. Yeah, personally, I think that this sort of dynamic generation of text is probably the way forward. But I don't maintain the books anymore, so it's not really up to me. All right, on to something a bit less stressful. So for the remainder of this talk, I'll be going over some of the stuff that we're doing at Genentech. And the first of these is providing multi-language support for bioconductor objects via our ArtifactDB system. The idea behind ArtifactDB is to provide a language-agnostic file representation for a range of bioconductor objects. So this includes delayed arrays, data frames, G-ranges, and so on, right? Most of these representations, are based around HTML5 and CSV, so we can easily read and write to them from other language, allowing us to extend our analyses to other frameworks like Python or web applications using JavaScript. Now, if you're doing all of your work in R, you might not really care about this interoperability, and you just say, hey, let's just save RDS files. The problem is that RDS files become quite difficult to handle once they get stale because, for example, a package developer changes the structure of their class. Then the old objects need to be updated to the new class structure, and you'd better hope that the developer added an appropriate update object method. And even if they did add an update object method, it might be expensive to run, or it might be deprecated at some point, or it might be buggy because these back compatibility issues tend to be hard to unit test. But with our artifact-DB formats, we avoid a tight coupling between the file and the internal structure of the class, because we only use the exported constructors and the methods for each class to restore the file format into an in-memory object. And that makes our infrastructure a lot more robust to changes to the class definition. One more benefit is that each bioconductor object is saved in a modular fashion. For example, a summarized experiment is broken down to its constituent assays and row and column data frames. And then that makes it possible to load in and work with parts of the object rather than being forced to load in the entire object at once, like you would have to do for an RDS file. And I'll talk a bit more about this in a few slides. So if you want to try it out, you can have a look at the Alabaster packages that are now available on BioC-Devel. So here's an example of me using Alabaster to save a delayed array. So here I've basically mocked up a delayed array containing a log normalized expression matrix. If we want to save this, we instruct, well, we basically instruct the Alabaster matrix package to preserve the delayed operations. Otherwise, it just saves it as a regular sparse matrix. And then we just call the stage object function to save our delayed array Y into this staging directory, this temporary staging directory. It also produces some metadata that we also save into the directory as a JSON file. So that gives us the sort of delayed array as a HDF5 file and a accompanying JSON file that I'll talk a bit more about later. Now that we have these files, we can copy them to someplace else or upload them to the cloud or whatever, and then a user can just get them, get those files, read in the metadata, and then call the load object function, and then boom, they get back the delayed array that they put in, basically. So it's a delayed array. It has the delayed operations, and then you can do pretty much the same thing in JavaScript as well to allow web applications, for example, to read delayed arrays in the browser. Here's another example of a G-ranges. So here I'm mocking up a G-ranges with some nice sequence information in the seq levels and some nice a name, some nice mcalls in the name and some metadata and the metadata, right? And then I just call the stage object function, and that saves everything to file. And you can see here that this produces a lot more files than in the delayed array example, because as I said before, each part of the object is saved to its own file. And then just somewhere downstream, a user can get all these files, call load object, and then they get back the original G ranges that we put in, which so you can see the name here and you can see the seq info. So that's looking nice and good. So the previous G ranges is a good example of our modular representation. The object is represented by the G ranges object is represented by the CSV file that contains the coordinates of the genomic intervals, their strandedness, and so on. And this file is itself a parent of a whole bunch of other files. So one of these child files contains the sequence information. Another child file contains the general metadata, and another file contains the mcalls, so the per interval metadata. And then each of them can in turn contain their own children. So for example, if we stored a nested data frame inside the mcalls of our G ranges, that would be represented as a child of the mcalls CSV. The modularity of this sort of object tree allows us to handle each part of the object independently. So for example, if we just want to update the seq info, or we just want to update the metadata or the mcalls, we can do so without changing the other files. And this is very nice for creating versioned databases, because we can just upload the modified files and create links to the unmodified files from the previous versions. Similarly, if I want to get the gene symbols from the mcalls or the names, I can just download the mcalls rather than being forced to parse this entire G ranges. So this is very helpful for making responsive web applications where bandwidth is at a premium. And finally, because we can assemble these objects in a very hierarchical way, we can easily construct representations for very complex objects. So for example, we can store a multi-assay experiment that stores a single cell experiment that has alternative experiments, that has summarized experiments, that has delayed arrays. And we can make very, very complex things that mirror or that reflect the in-memory representation in an R session. You might have noticed that all of the files in the previous slide were accompanied by a JSON file. This JSON file contains all the metadata for each data file, describing what the file contains, how to read it in, is it compressed, what its children are, what the checksum is, and so on. So by reading the metadata, packages like Alabaster or the equivalents in Python and JavaScript can figure out how to load the file into an appropriate byconductor object. The expectation, I will say, the expectation for this JSON metadata is defined by a schema. So on the right here, I've got the schema for a genomic ranges object. So this defines what the required fields are, basically what the type of the fields are, whether they're strings or integers or whatever, and various other constraints. And whenever any user saves an object, each metadata JSON file is automatically validated against this schema when they try to write it to disk. And if that metadata is not valid, the write operation fails. So this ensures that all the files saved to our database have the correct metadata, which provides some guarantees to downstream packages that they can that they are guaranteed to have, for example, the compression field, so that they know how to interpret the files. I'll add that it is possible to define your own metadata requirements to the schemas. For example, this single cell experiment schema is actually taken from a database that tries to mimic Experiment Hub. So you can see that it contains additional fields like author, title, description, species, and so on. So for example, if you were in charge of a database for, I don't know, a drug company, you might add more fields like identifiers for clinical trials, links to other clinical databases, and so on. Then whenever a user wants to save a data set to your database, they have to make sure that all these fields are filled out correctly before saving their objects. The final thing I'll say is that, in all of the code I was showing previously, we were just saving and loading from the local file system, but there's no need to be limited to one computer. The ArtifactDB system is fully cloud native, so you can read and write from cloud resources for global accessibility. So my colleague Sebastian has developed the corresponding backend infrastructure using AWS 3 for file storage and Elasticsearch for storing and serving metadata. And this provides a bunch of the expected database features like permissioning, versioning, search on metadata, and partial updates for objects. All of this is wrapped using a REST API, so client packages in various languages such as Alabaster for R can call this API instead of using the local file system. And this allows us to very easily share objects between users across different compute environments, so different laptops or HPCs or cloud computing or whatever, right? And I would say that this system has proven itself across a range of use cases inside the company, and I've listed a few of these here. And actually, we're currently working with the byconductor core team to set up a test instance using an ArtifactDB to create a multi-language annotation hub. So if you're interested in setting up an instance for your own organization, just reach out to us. I'm going to skip all of this because mostly because I've talked about it before, and also because we're running out of time. But if anyone wants to listen to the full version, go to I think the Byconductor Asia 2022 talk is available online on YouTube, so you can go check that out. I'm just going to skip this, blah, blah, blah. And yeah, just to wrap up, I'm going to skip. There's a couple of fun things that I haven't talked about, but if anyone's interested in these, I can talk about them a bit more. And I'll just finish by acknowledging many of the folks who are involved in these projects. So OSCA, so Rob, obviously, for kicking it off, and a whole bunch of people from the community for chipping in with various things every now and then. ArtifactDB is driven by my colleague Sebastian, and JRM is responsible for the Python interfaces to that system. Yeah, I didn't talk about this, but Canna, Jay and I have been working a lot on that. And version 3 is coming out soon with feature sets and an explore-only mode. So keep your eyes peeled for that. Yeah, and with that, that's pretty much it. Sorry for running a bit over time, but yeah, happy to take any questions.
Cool. Thank you so much, Aaron, for this super interesting and always very entertaining talk. Just one quick question. Are you sharing these slides at all?
You mean on my screen? Because
no,
I hope
these slides. Are you going to share these slides?
That I can do that. Yeah.
Okay, cool. Okay, so are there any questions for Aaron? There were a couple of questions and comments already from Vince in the chat, but if folks have questions, please feel free to ask and raise a hand. Maybe I start with one question out of own interest on the OSCA book, Aaron. What is the approach for like new contributions? Obviously, a single cell analysis is a moving field. There are a lot of like new interesting methods coming out, and I think now there's one person who asked about adding something on the multiplexing. How have you dealt with such like requests in the past? Should we? You described all these compilation troubles and bringing in new dependencies that have the tendency to break the book. Should we just keep the book self-contained as it is right now? Should we be open to new contributions? What kind of criteria have you applied in the past? Like, have you screened them for quality? I think you also maybe have looked at like runtime of these contributions, that they like run in some sort of a minute or something, that they fit in. I just wonder whether you can elaborate on this a little bit. I saw you gave the blessing with the thumbs up of this particular request there on a GitHub issue, and I was wondering.
Yeah. So philosophically, I greatly approve of any contributions from the community. I speak mostly philosophically because it's been so hard to get people to contribute. Especially after the paper was published, it was like people just disappeared. But anyway, definitely, I think we should we should encourage contributions. That was in fact the whole point of moving it out of the workflow package and getting it into the book. The whole point was to have a single bioconductor resource that people could contribute to. In terms of screening, there's been a few cases where I've tried to use someone else's package, but it took too long. And I think this is actually I think if it takes too long, it's a good feedback to the package developer that perhaps they should improve something, right? And I think that's actually it's a good motivation, right, to get package developers to write efficient, to improve their package so that it runs faster. In terms of the sort of quality of the contributed sort of book, usually, at least for me, I just go over and rewrite all the text to fit into my writing style. But as the contributors become more heterogeneous, I think it's probably okay that people have different writing styles, and that's not too bad, right? But usually, as long as they have like appropriate fail safes to match up to their text, it can go through the usual, usual PR and review process. And I think we should, I think we should not disallow contributions. I think if people are looking forward to contribute, we should allow them to do.
Okay, great. And maybe on to Vince's question on the coverage of these fail-safe tests. Did you is there anything in place that would allow to kind of like measure how many chunks have such fail-safe tests? Vince puts here some lines that ask whether those could be put into functions and whether something like cover could be used for that.
I don't know of a easy way to do that, other than like obviously inserting our own hooks into to mark coverage. But I also don't write a lot of coverage tools. I use them, but I don't write them, so I'm also not sure how I would go about doing that. I never really thought about that too much, to be honest.
Aaron, wonderful talk. I wanted to run just a couple of things by you. First of all, this notion that the book paralyzed your coding is really disturbing to me, and I'm sad about that. I can understand where it's coming from, but it seems to me we have to make a much more integrated effort to ensure that the software that's being discussed in the book can evolve at the rate that it's supposed to evolve. Would you agree with that proposition? I agree. If we could get support for that.
I agree with that. And that was it does occur to me that maintaining this book and keeping it running is basically someone's, if not full-time job, at least a part-time job, right? And I do this on, like, it's definitely not my job because I do it on the weekends and the evenings, right? But
It's definitely something where dedicated support would be needed. And I guess, when you think about book publishers, they get the thing out the door and they don't really have to worry about it. And this is a completely different situation.
Yeah.
I wanted to ask, I recently thought about Markdown render versus Markdown run as a way of dealing with an educational artifact. And I'm sure you're familiar with Markdown run, where you can have apps embedded in the Markdown that allow the user not just to read what you've written, but also to try other things interactively.
Mm-hmm.
Have you given any thought to that as a basis for a different type of pedagogic artifact?
I'm actually, so our Markdown run probably still calls a backend, right?
That's right. You have to be running it on a server. But if you have that, is it something that would enlarge the teaching and learning capabilities in a meaningful way? My suspicion is that it would, but it's another commitment.
Yeah, it would. It'll be interesting to see how the RStudio's WebR stuff pops out, because then they could run it client side. Not sure if they want to, but I guess we run Can. Yeah, well, I mean, Can is quite optimized, so that's a different story. But I think a lot of things wouldn't quite work as expected with WebR. But I don't know. It could be very interesting to see whether that would work.
One of the reasons that I thought about this is the idea that some of the text in the book might be cherry picking. You've really shown people the best example of what it is you're trying to make.
Yeah.
And if you allow people to poke around and say, oh, that actually is more general than it looks, that's pretty valuable.
Yeah.
Other questions for Aaron? If not, maybe shortly back to these additional contributions, Aaron, I was wondering, in your opinion, what would be like areas or avenues where you would think there would make a lot of sense to like add additional stuff? Well, apparently there's a lot of development in cell type annotation. There's a bunch of new papers out on like differential expression testing in a cluster-free context. This whole multi-sample, multimodal, where do you think would it make sense for like folks that are now maintaining the book to put a focus on like extensions to the book?
Right. Probably the multimodal chapter could use a lot of love, right? I won't say I just pulled stuff out of my ass, but it was getting close to that, right? Because I was like, well, let's put this different thing in. I really should have put an under construction section for that chapter. Cell type annotation, for sure. I'm probably talking about like different references and stuff like that. There's also I tried to, like, a long time ago, I tried to reach out to the Archer authors to see whether they'd be interested in having a taxi incorporated into the book, but they had their own book, so it wasn't a priority for them.
There's an issue that I think we need to contemplate, though, which is deprecation. So the book is really great, it's fixed in time, but maybe some of the things that are being endorsed there are just not supposed to be used anymore. Is anybody looking at that, thinking about how to pull things out if they aren't the right way to go anymore?
No, I guess the answer is yeah.
Another question from Tyrone.
A little bit less on the ARC side, but maybe more on the production stuff. As it's interesting that you had some various slimmed down versions, like the slimmed down scran that you put on by OSCA. So I'm just curious, how do you is this necessary in order to get around certain performance bottlenecks in your workflow? Because a lot of it could be down to how Nitto works. I have a hard time trying to get workflows to get around either Pandoc or Knitter. So I'm trying to figure out whether the answer is just slim down everything in the code, or if there is some other tricks that you may have found.
Yeah, the Scran-Chan package is not particularly related to the Knitter any problems with Knitter. It's more the existence of the Scran-Chan package is motivated by the fact that all the existing infrastructure that I have is extremely tightly tied to delayed arrays on the R side, whereas Scran-Chan moves the delayed arrays onto the C++ side. And that kind of, doing that kind of shift in place would just have been very difficult while preserving the same set of results. So that's why Scran-Chan exists. It doesn't really have I didn't write Scran-Chan to get Knitter to fix any problem related to Knitter. Even though I did have a few problems related to Knitter, but that was kind of unrelated.
Okay.
Okay, great. So I think we're at time. I don't know, Vince, while you're at it, do you still want to get this comment on the seek info in there, like the validating of the
no, I mean, yeah, okay, so here's the question. You mentioned how the modularity permits you to make, component-specific changes, but it seemed to me like you didn't have an integrity check. Once those components were changed, do you check that the whole object is consistent?
Yeah, so the R package will do that. The R package will do that. So actually, what happens when the R package will actually transparently find, you have your entire G ranges. The typical process is a user loads in a G ranges. They might, for example, modify the seek info, right, and then they save that object back again, right? So that modification of the seek info is validated by the G ranges itself, right? And then in the saving process, what happened is that in this case, the database will detect that the saved files like some of the saved files are the same, and it will only upload the modified files, in this case for the seek info, to the backend, right? So that's how in the R case, that's how it handles it, right? We just rely on genomic ranges itself to provide the validation.
Yeah. Okay, well, I don't want to be tedious, but it seemed to me like one of the possibilities was to change the CSV data, if that's what's down on disk, on its own, in some other language potentially, and then just put back the revision. Would that be validated?
Not on the backend side. So if you do have like malicious uploaders who aren't respecting the sort of contract, then yeah, anything. It's not sort of defensive against that sort of abuse, right?
Well, all right. Well, then thanks so much, Aaron. I think we're all thanking you for your time.